Dear students, this is electromagnetic course. The topic code is EMWG-S5. The title of the topic is Skin Effect and Skin Depth. Further, within this topic, we will be discussing the penetration of high frequency electromagnetic fields into a good conductor. Let us first define the skin effect. Skin effect is the tendency of an alternating current to become distributed within a conductor such that the current density is the largest near the surface of a conductor at the highest frequency. When the frequency is the highest, so the current density is the largest near the surface and decreases with the greater depths in the conductor. Or we can define this phenomena in another way, that is the gradual shift of the alternating current from the center to the surface of a conductor due to the increase in the frequency is known as skin effect. In a moment I am going to explain it with the slide as well. Let's first go through the definition first. While the skin depth is a measure of the depth of a conductor at which the current density falls to 1 by E of its value near the surface, that is 37% of the peak value. So these are the definitions. Now let's see that how we take this phenomena inside the conductors. Again, we look at the skin effect tendency. It is the tendency of alternating current AC to become distributed within the conductor such that the current density is the largest near the surface of the conductor and decreases with its greater depths, as we already defined. The skin depth is the measure of the depth at which the current density falls to the 1 by E of its value near the surface. Skin depth is also described as exponential decay of the electric and magnetic fields, as well as the density of the induced currents, and also the distribution of the current flow in a cylindrical conductor. For alternating current, most 63% of the electric current flows between the surface and the skin depth. Now let's see just one more here. What happens that when the alternating current flows here, what it does, we have the induced, it induces the eddy currents. So alternating current IT, as you can see, that is instantaneous, the alternating current. So there are magnetic field in the conductors. Basically the conductor is made of the atom and the molecules. They have the magnetic moments. So when the current passes through, the field associated with this current agitates the magnetic moments, and those agitations causes the eddy currents, where swaying the magnetic moments the one direction and the other direction, and these eddy currents are causing the rather a resistance reactance inside the material. So what happens that in this conductor, you can see that with the higher the frequency, the area of cross section for the flow of the charge is reduced. Here we can see that the charges are pushed towards the current is pushed towards the surface area, surface of this cylindrical conductor. We have taken the slice cross sectional through the radial part. We have cut it into two pieces. So here the current is flowing closer to the walls or the surface, while the inner region is being vacated due to the here very strong agitation of the eddy currents or induced eddy currents. So the available area is now this. So that is the phenomena of we say skin effect. We have the This is the slide which shows the constant current it flows along the some conductor which is having the cylindrical shape or the geometry. The constant current flows throughout the area of cross section of the cylinder. While in this case, alternating current when flows with a higher frequency, you can see the exponential decay of the current density takes place. So the larger current will be flowing close to the surface, smaller current closer to the center. Away from the center, the current is flowing at a. Here is another illustration of skin effect and skin depth. Let us take this a copper wire. This is a cylindrical copper wire whose cross section area is being shown, and it has the radius of 10 millimeter. For now, you see for DC current, no skin effect, no skin depth or skin effect phenomena is observed. All the area of cross section is available for the current, for the flow. Whole of the area is available. Now, if the frequency, if we allow the current which is of the frequency 50 Hertz, the skin depth for that this wire will be 9.3 mm. So very slight, you can see a very small here impedance is being observed. A small area cross section is being here being void of these charges, or the charges will flow still pretty considerable 9.3 mm radius of the cross section. You can find the area of cross section by pi r square in this particular case. Now, if the frequency is increased to 10 gigahertz, now you see the skin depth is 0.65 microns, micrometer. You see here, it's a very small ring. You can see it's almost the skin of the whole, this cylindrical surface. So the current flows in this small region, in this small area, which is of the 0.65 micrometer. The length or the width. So at a higher frequency, you can see the current is pushed to the surface almost, and the current flows on the surface only, while the rest of the whole area of cross section of the wire is not utilized. That's why in communication or the transmission lines, whatever the wires are used, they are tube type wire, where only the current is flowing on the surface of that conductor. The idea about it. Now let's move on to the penetration of the high frequency. We are going to now derive the relation for the skin depth as well. So the penetration of the high frequency electromagnetic fields into a conductor. Now let us consider those conductors who obey Ohm's law. This is the field form of the Ohm law. J is equal to sigma C times E. We have already discussed that, how we get this relation. E is equal to IR. We can set moved from the Ohm law to this field Ohm law. That is circuital Ohm law. This is the field Ohm law, the electromagnetic field wave Ohm law. So we have the current density J is equal to sigma C, where sigma C is the conductivity. Now we have Maxwell equations given as curl of H, which is the curl of Ampere's law, is equal to J plus delta D by delta T, while D is given as D naught is for J omega T, and E is equal to E naught is for J omega T. H is equal to H naught is for J omega T. So curl of H, now putting the value of these respective delta D by delta T, taking the differential, and also the J value, which is sigma, here sigma is E. So if you put the values, we get this, and simplify it, we get the expression, which is equation number 2. Equation number 1 is the Ohm's law. So the curl of H is equal to sigma plus J omega epsilon E. Equation number 2 we got. Now in the absence of the charges, rho is equal to 0. Divergence of E is equal to, we are talking about the propagation of the electromagnetic wave in the free space first, and when they will hit, you will see over there how it takes place. But if we have the whatever the Gaussian surface you take, it is not containing the source charge density is 0, then divergence of E will be equal to 0. So we assume that there exists the homogeneity of the sigma and epsilon. They are homogeneous, they are linear, they are isotropic. The medium is behaving, whatever the inside the property of the medium is, they are behaving properly, they are uniform in their response, whether this electrical response, chemical response, or any type of the mass, the density of the material. Now to derive the differential equation which determines the penetration of the field in the conductor, we take now the curl of E is equal to, this is famous, we have the Faraday law, given as the curl of E is equal to minus delta B by delta T. B is again is equal to mu H. Curl of E is equal to minus J omega mu H. This is equation number 3. Now taking the curl of the both sides of equation 3, so we get the curl of E minus J omega mu curl of H. So that we have the applying to the left hand side the vector identity, that is curl of E is equal to the gradient of the divergence of E minus del square E. Since divergence of E we have taken equal to 0, so we are left with this equation, final equation after simplifying and the cancelling the like negative sign. Del square of E is equal to J omega mu sigma E is equation number 5. So what we have, the similarly for the del square of H, we have the equal to J omega mu sigma H, are putting the J is equal to sigma E, or E is equal to J by sigma in equation number 5. In this equation, if we put the E value, which is E J by sigma, so what we get, the del square of J is equal to J omega mu J current density in equation number 7. So since sigma is constant, we are not changing, so it is cancelled out from both sides. We are left with so we have got 3 equations, one for the E, other for the H, and one for the J. Now let us consider consider a uniform field situation with electric field moving along the positive Z direction, as this is the case, EX and with EX and HY components. So the propagating E field is Ez delta d2 by dx square, because Ex is now along the varying the propagating along the, that is the transverse to the x, is equal to J omega mu sigma Ez. The last equation we have here, this one, we just simplifying it, putting it into the component form, which is the Ex component. Rest is we are putting Ez, we get the delta Ez by delta x square. So let's take this term whole J omega mu sigma as a tau square. Then we will have the second order differential of the Ez is equal to tau square Ez, equation number 8, and tau square is equation number 9. We can write also J as 1 plus J divided by 2 square root whole square. If you open that up, you will get again the J value. So under root, if taking the square root of both sides, we get the under root of J is equal to 1 plus J over under root 2. So tau can be written as J instead of under root J. We can take that out from that. We are solving for the tau at the moment. Then the J is taken out. We can write instead of J under root J 1 plus J over 2 square root into omega mu sigma. Or we can put omega is equal to 2 pi f. 2 we can cancel out, this is square root, another square root, this is also square root, they cancel out. We are left with the 1 plus J into pi f mu sigma. Or we can write 1 plus J over delta, where delta is 1 over pi f mu sigma, and delta is called now, this is called now the skin depth. Delta is equal to 1 over pi f mu sigma. square root. It has the unit of the meter. This is equation number 11. Now the complete solution of equation 8 is of the form given as Ez is equal to C1 e to the power minus tau x plus C2 e to the power plus tau x. This is equation number 12. Now at x is equal to infinity, if we put the x as infinite distance, the Ez will increase to impossible value. So that if x is infinity, so what we'll get, e to the power infinity is infinity, so it is not possible that Ez is infinite. So what we have, so unless C2 is 0, so at that value C2 is a constant, we will put equal to 0. C2 value has a 0 value, so that we can reduce that the undefined situation, that is the we call singularity. We don't want that into a particular situation. So, and the coefficient C1 is can be considered as the amplitude E0, amplitude of the field. So Ez is the field equation now is given as E0 is for minus tau x. So putting the value of the, now these are the boundary conditions we applied. So the the tau value is 1 plus j over delta. So if further you split that up, Ez is equal to E0 is for minus x over delta is for minus j x by delta. So if you take the, similarly Hy is equal to H0 is for minus x by delta is for minus j x by delta. Jz is equal to J0 is for x minus x by delta and is for minus j x by delta. These are the equation 15 and 16. Now the magnetic field and the current density are governed by the same differential equations as the E field. Conclusion is that it is evident from the equation 14, the last E field equation we have got, this one, the 14, from 14 to 16, that the magnitudes of the fields and the current decreases exponentially with the penetration into the conductor, and delta has the significance of the depth at which they have decreased to 1 over E, that is 36.9 or around 37% of their peak values at the surface. Now the quantity delta is called the depth of the penetration or skin depth. Now if we take the absolute value of this Ez, and we have already demonstrated that the absolute value of a E exponential part is a unity. Over there we take the psi star is equal to 1, the psi square we take. So we have in this exponential, if psi is an exponential function, its conjugate we take and multiply it with that function, so that is equal to unity. So we are left with this E0 is to minus x by delta. Now at x is equal to delta, when this x distance becomes equal to the delta, what we get, Ez is equal to E0 e to the power minus 1, or E0 over E, or it is 0.369 E, or 37% of the E0. Thus we get the conclusion that it is the 37% of the maximum of E0 at x is equal to, that is the maximum value at the surface. Now this is the example already I have demonstrated that the same current with the zero frequency, all the current is flowing through, current density is uniform throughout the cross section of area of the cylinder. In this case there is the skin depth, and the larger current is flowing close to the walls, while the less current is dying to the center, close to center. These are some examples or the data regarding the material skin depth at various frequencies. This is at 10 gigahertz, and this is at 60 and 50 hertz only. So aluminum is 0.8 micrometer. I don't have the data for 50 hertz or 60 hertz, but for copper 0.65 micrometer it is. Now here is for 50 hertz it is 9,300 micrometer, and for 60 hertz is 8,470 micrometer. Gold is 0.79 micrometer. For 10 gigahertz, remember, silver has 0.64 micrometer. So with this we reach to the end of the topic. Inshallah we'll meet again with another new topic next time. Till then, Allah Hafiz and thank you.